Part 1. Graphing.
Yo, check it out. Section A, the unit circle.
Before we show you how to graph trig functions, let's first go back. Now, think way back. Way back.
Not that far. There you go. Back to the quadrants we talked about earlier.
Before graphing some curves, we first need to talk some about angles and points in quadrants.
Actually, we want to show you how you can have positive angles with negative values. This will be important when we graph trig functions. We'll explain what all this means. Let's take a look.
We're going to start by drawing a circle on a coordinate graph. To keep things simple, we'll just give this circle a radius of 1 unit. Remember from your geometry class that the radius is the distance from the center of the circle to the end of the circle. Anytime a circle has a radius of 1, it's called a unit circle. Next, we're going to draw an angle in quadrant 1 of the coordinate graph. We're going to call this angle T.
Okay, do you see this point where the terminal side of angle T intersects with the circle? We'll call this intersection point P. If you remember your algebra, you remember that every point has an x and y coordinate. The coordinates represent how far you travel from the origin of the coordinate graph to points up or down on the y-axis and to the left or right on the x-axis.
And just one more quick reminder. All y-coordinates are positive above the x-axis. X-coordinates are positive to the right of the y-axis. You're going to find an x and y coordinate for this point P. The distance of point P from the x and y-axis is what gives us point P's 2 coordinates.
Hey, dudes, I don't know anything about radians or pies, but I do know a lot about amplitude. Turn it up, Anton, and I know I like it loud. Oh, yeah!
Okay, so now we have this angle T in the first quadrant of a coordinate graph. And that angle is also part of a unit circle. What now? Let's go back to the circle.
The next thing we have to do is drop a perpendicular line from point P back down to the initial side of angle T. And there we have a right triangle. Why'd we do this?
Well, because now we've got a right triangle. I'm sure the unit circle was a completely weird-looking thing that was totally intimidating. But there's nothing intimidating about a right triangle. We already know how to solve those.
So far, we've talked about how sine and cosine are trig functions. Now we're going to use these elastic little suckers as x and y coordinates. Don't worry, we'll explain.
We've just made a right triangle on our unit circle. Now that we have a right triangle, we can go back to our definitions for sine and cosine.
I think I might have forgotten what you just said.
No worries. Just remember SOHCAHTOA.
The cosine of an angle, or t in this case, equals the adjacent side over the hypotenuse. Check it out. We know the hypotenuse of our triangle, or the radius of the circle, is equal to 1. So we can plug in 1 for the hypotenuse, which is the denominator, giving us the cosine of t is equal to the adjacent side over 1. So the cosine of t equals the length of the adjacent side on our right triangle. In other words, the length from the vertex here to the end of our right triangle here on the x-axis is the cosine of t. This is our first coordinate for point P, coordinate x. That's because the x-coordinate is the length of our adjacent side, or the cosine of t.
Now we're going to do the same thing for the y-coordinate.
Now think back to the sine of an angle. Remember that the sine of t equals the opposite side over the hypotenuse. We know the hypotenuse is 1, so we stick this amount into the bottom of our fraction. The sine of t equals the opposite side over 1. So the sine of t is equal to the length of the opposite side of the right triangle. So the sine of t, or the opposite side, is our y-coordinate. That's because the y-coordinate represents the height of the opposite side.
This means that point P has a cosine of t for the first coordinate and a sine of t for the second coordinate.
I know all this seems a little random, but now that we know that the cosine of t is the x-coordinate and the sine is the y-coordinate, we can find out what happens when the size of angle t increases. And this will make some things easier when we get to graphing. I know you're excited, so let's get started.
If angle T terminates in quadrant 2 between 90 and 180 degrees, like this 130 degree angle does, then the x-coordinate of P is always negative and the y-coordinate of P is always positive. Remember, we just figured out that the x-coordinate for our angle is equal to the cosine of t and the y-coordinate is equal to the sine of t. This means that the cosine of t is less than 0 and the sine of t is greater than 0 in quadrant 2. So the cosine of a 130 degree angle, or any angle in quadrant 2, is negative while its sine is positive.
You can check this out for yourself on your calculator.
Now, if angle T terminates in quadrant 3, then both coordinates are negative, so that the cosine of t and the sine of t are both less than 0. So the cosine and sine of any angle in quadrant 3 is always going to be negative. Remember that.
And finally, if t terminates in quadrant 4, then the x-coordinate is positive and the y-coordinate is negative. So the cosine of t is greater than 0, while the sine of t is less than 0.
Okay, the reason we've been doing all this is coming up. This is important, so listen closely.
Notice that as angle T moves into quadrants 3 and 4, or becomes greater than 180 degrees, or pi radians, the sine of T is less than 0. Even though angle T is a positive angle, point P has a negative coordinate for the sine of T. That's because the sine of angle T is the y-coordinate, and when you're in quadrants 3 and 4, the y-coordinate is negative.
When we're graphing the sine function in the next section, you'll see this happen again. When we're graphing the sine function in the next section, you'll see this happen again.
So don't forget, the sine of an angle is negative in quadrants 3 and 4, or between pi radians and 2 pi radians. And the cosine of an angle is negative in quadrants 2 and 3, or between pi over 2 radians and 3 pi over 2.